Solving systems of linear equations. Let's take a look at some examples of each type. Solve the system of linear equations graphically. Solve the system x plus 2y equals 0 and 2x minus 3y equals negative 14. Remember, you should be able to identify which type of solution you have. That is, either a unique solution, a single point of intersection, an inconsistent system, which is the parallel case, or the dependent system, which has an infinite number of solutions. If we take each of the two equations and solve for y, in other words, putting them into the slope-intercept form, that will give us y equals negative 1/2 x and y equals 3/2 x plus 14/3. We can use our calculator to graph these after we have attempted to graph these on a piece of graph paper by plotting points. Using the calculator here or using the graph, we can see that the point of intersection is the point negative 4 and 2. Example 2. Solve the system of equations graphically. The system here is 3x minus y equals 1 and 4x minus 3y equals 3. Once again, graph the two systems by plotting some points and connecting them as we have done in earlier sections, or by putting the two equations into the slope-intercept form and using the calculator to graph them. We can take the two equations in slope-intercept form, y equals 3x minus 1 and y equals 4/3 x minus 1, and graph them. We can see here that the common point of intersection is the point 0, negative 1. So once again, we have a consistent system. Next example. Solve the system of equations by the substitution method. Let's take the equations 6x plus 5y equals 1 and x minus 3y equals 4. Solution. We're going to take equation 2, x minus 3y equals 4, and solve for x and substitute that back into the first equation. Simplifying and solving for y gives us y equals negative 1. Now if we take y equals negative 1 and solve that into the other equation, we get the solution 1, negative 1, which of course is a consistent system. Next example. Solve the system of equations by substitution. Again, 4x minus y equals 3 and 3x minus y equals 1. Take the first equation, solve for y, and substitute that into the second equation. Simplifying and solving for y, we get y equals 5. If we take y equals 5 and substitute that into the second equation, we get x is equal to 2. Therefore, the solution to the system is the point 2, 5. Again, a consistent system. Next example. Solve the system of equations by the addition method. 3x minus 4y equals 11 and 3x plus 5y equals negative 1. Solution. We'll take the first equation and multiply through by negative 1. This gives us negative 3x plus 4y equals negative 11. And we will add that to the second equation, 3x plus 5y equals negative 7. Adding, we see that the x variable is eliminated, and simplifying and solving for y, we get y equals negative 2. Substituting y equals negative 2 back into the first equation yields x equals 1. So therefore, our point of intersection is the point 1, negative 2. Again, a consistent system. Solve the next system again by the addition method. 4x minus 2y equals 6 and 4y equals 8x minus 12. Let's first make sure that both equations are in standard form. Doing that, we see that negative 8x plus 4y equals negative 12, and positive 8x minus 4y equals negative 12. This yields 0 equals 0 when we add the equations together, which, by the way, is a true statement, but that means that we have a dependent system, an infinite number of solutions. You can stop right there by identifying the fact that we have a dependent system. An applied problem. Benjamin's backpacks sell for $25 per backpack, and the cost of manufacturing are a fixed cost of $400 and a production cost of $15 per backpack. We end up with the two equations, that is, cost equals 15x plus 400, and 25x is equal to the revenue equation. If we set those two equations equal to each other and find the point of intersection by any method, although you can see a graph in front of you, we see that the point of intersection is the point x equals 40 and y equals 1000. Here x is equal to 40 means the number of backpacks that must be manufactured and sold in order to break even is 40, and that the cost and the revenue at that point is $1,000. Let's take a look at a profit formula. Since the definition of profit is revenue minus cost, we see that 25x minus the quantity of 15x plus 400 simplified gives us a profit equation of 10x minus 400. Use our profit formula to calculate whether the profit for 30 backpacks manufactured and sold would be a positive or negative profit. Negative profit, of course, means that we have a loss. If we substitute x equals 30 into our profit formula above, we see that we have a profit of negative $100, which is, of course, a loss. How many backpacks must Benjamin's backpacks sell in order to realize a profit of a positive $1,000? Once again, we will set our profit equation equal to 1,000, simplify, and solve for x, which leads us to 140 backpacks. Next example. Pizza Hut sells both medium and large pizzas. The medium Meat Lovers sells for $10.95 and the large Meat Lovers sells for $14.95. On a particular Saturday, 50 Meat Lover pizzas were sold, and the receipts for the sales were $663.50. How many of each type were made and sold on that particular night? In this case, we're going to take a single variable approach. We're going to let x equal to the number of medium pizzas, and we're going to let 50 minus x equal to the number of large pizzas. We're then going to use the revenue generated by the sale of each type of pizza to solve the problem. Here we have 10.95x plus 14.95 times the quantity 50 minus x equals 663.50. Simplifying, we get a solution of x equals 21. Taking the 21 and subtracting that from 50 means that we have sold 29 large pizzas and 21 medium pizzas in order to satisfy the constraints in the problem. Well,